Before programmers wrote a single line of code, before electricity even reached most American factories, machinists were cutting threads so perfect that NASA still uses parts made on these machines today. But how did bronze gears think in mathematics that computers wouldn't invent for another 50 years? Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. Hartford, Connecticut, 1915. The screw-cutting lathe sat in the corner of Pratt & Whitney's tool room like a mechanical oracle, its headstock packed with gear trains that could divide circles into mathematical relationships no calculator had yet computed. Thomas Warner ran his calloused fingers across the change gear quadrant, selecting combinations from the 60 bronze gears hanging on the wall like a metalworker's abacus. 29 threads per inch, the foreman had said, handing Warner a blueprint for a rifle barrel blank. An odd number, prime, the kind of specification that made apprentices nervous because it couldn't be factored neatly into the simple ratios most lathes cut naturally. Warner pulled down a 127 tooth gear, the magic number that unlocked metric conversions when American lathes still thought in inches. He paired it with a 29-tooth gear, creating a mechanical fraction that would force the lathe's lead screw to rotate exactly 29 times for every complete revolution of the workpiece. No electricity, no programming, just cast bronze teeth meshing with mathematical certainty. The workshop smelled of cutting oil and hot metal. Steam engines in the basement drove line shafts that ran the length of the building, leather belts, transferring power to individual machines through stepped cone pulleys, but the real intelligence lived in the gear trains, cascading ratios that transformed simple rotation into complex, helical motion. Warner's lathe was a Hendy, built in Torrington when American machine tool builders still signed their castings like artists. The bed stretched 8 feet, its ways hand-scraped to flatness measured in 10,000ths of an inch. But the headstock contained the real magic, a Norton-style quick-change gearbox that let machinists select thread pitches by moving a single lever, rearranging gear meshes hidden inside the cast-iron housing. Most machinists in 1915 didn't understand how the gearbox worked. They just knew which lever positions cut which threads. But Warner had apprenticed under men who remembered when every thread pitch required manually calculating and installing change gears, converting the ratio between spindle and lead screw into physical combinations of bronze teeth. He engaged the half nut that connected the carriage to the rotating lead screw, watching as the cutting tool began its journey along the barrel blank. The lathe cut threads by maintaining a fixed relationship between rotation and translation, spin the work 29 times while the tool advances exactly 1 inch. Simple as ratio, precise as geometry. Across the Atlantic, British machine shops wrestled with the same mathematical challenges. But here in Hartford's Precision District, American builders had standardized the solutions, casting mechanical intelligence into machines that would outlast their creators by a century. The Brown & Sharp universal milling machine had been cutting gears since before the Spanish-American War, and Robert Chen still marveled at its spiral head attachment, a device that could generate helical grooves without ever being told what a helix was. Chen mounted the gear blank in the dividing head, a mechanical indexing device that looked like a small safe with a handle. Inside, a 40-to-1 worm gear reduction let him rotate the workpiece by precise fractions of a circle. Want to cut a 37-tooth gear, divide 40 by 37, get the fractional turns needed, then set up the index plate accordingly. But cutting spiral gears required synchronized motion in 3 axes simultaneously. The cutter had to advance along the workpiece while the blank rotated at a precise helical angle. Brown & Sharp's solution was mechanically elegant. Connect the table's lead screw to the dividing head's worm shaft through a train of change gears, creating a fixed relationship between linear table motion and rotational blank motion. The geometry lived entirely in the gear ratios. A 24-tooth gear meshing with a 40-tooth gear created a 3.5 ratio. Stack multiple gear pairs and you could generate any helical angle the mathematics demanded. No computer calculated the path. The machine simply followed the physical constraints built into its mechanism. Chen had seen the new cam-operated automatic screw machines at the Acme factory. mechanical. Marvels that could perform 15 sequential operations on a brass fitting without human intervention. Master machinists would spend days setting up the cams, creating physical programs etched into hardened steel cylinders. Each cam was a frozen moment of human decision-making. The machinist would calculate when the cross-slide needed to advance, when the turret should index to the next tool, when the collet should open to eject the finished part. Then he'd cut those decisions into cam profiles, rising surfaces that pushed followers at precisely calculated moments in the machine's rotation cycle. A single camshaft might orchestrate 8 different motions, each cam stacked along the shaft's length like chapters in a mechanical book. The machine read this program at whatever speed the operator ran the line shaft. Faster rotation meant faster production, but the sequence remained locked into the cam geometry. Warner had watched Acme machinists profiling new cams using master templates and sign bars to generate complex curves that would guide cutting tools through three-dimensional space. The best cam cutters could look at a part blueprint and visualize the cam profiles needed, translating engineering drawings into physical automation without writing a single equation. The intelligence wasn't in the machine. It was in the machinist who programmed it with files, grinders, and geometric intuition refined through years of cutting metal. The Blanchard lathe had been cutting gunstock since 1820, and in 1915 it still embarrassed every attempt to explain how it worked using mathematics alone. Joshua Mills stood in the Springfield Armory's wood shop watching the machine trace a master pattern while simultaneously cutting an identical shape in rough maple. 2 spinning workpieces. One was the master, a finished gun stock carved by hand to perfect proportions. The other was a blank that would become its twin. A follower wheel rode against the master's surface, while a cutting wheel positioned at exactly the same geometric relationship carved into the blank. As the follower climbed hills on the master, the cutter duplicated those hills on the workpiece. Pure analog computation. The machine solved three-dimensional copying problems that wouldn't see mathematical notation until decades later, when computer programmers struggled to describe surface contours in digital coordinates. Thomas Blanchard's genius wasn't mathematical, it was geometrical, translating spatial relationships into mechanical linkages that maintain proportions without calculation. Mills had studied the mechanism's drawings, tracing how 16 different motions coordinated through nothing but shafts, gears, and linkages. The work rotated. The follower arm swept across the master. The cutting wheel advanced and retracted based on the follower's vertical position. Every motion mechanically locked to every other motion through fixed geometric relationships. Across the shop, a Cincinnati planer pushed a 4,000-pound table back and forth under a cutting tool with such perfect straightness that machinists used it as a reference surface. The machine's ways were hand-scraped to create bearing surfaces that defined flatness itself, not measured against some external standard, but established through the mutual agreement of 3 surface plates checking each other. This was the foundation of all precision. Geometric relationships bootstrapped from careful observation. Machinists created flat surfaces by scraping 3 plates until each claimed the other 2 were flat. They made straight edges by checking them against surface plates. They verified squares by rotating them and looking for deviations that revealed geometric error. Oskar Kellenberger in Switzerland was building cylindrical grinders that held roundness to millionths of an inch using the same principle. Geometric relationships maintained through mechanical constraints, not measured by instruments, but embodied in the machine structure itself. Mills picked up a Starrett combination square, its blade precisely perpendicular to its head, because both were ground against reference surfaces whose accuracy traced back through generations of careful comparison. The square didn't know it was 90 degrees. It just was, defined by its relationship to other precisely made objects in an interconnected web of geometric truth. No equations required, just metal ground against metal until the geometry emerged from mutual agreement, bootstrap precision pulling itself up from careful craftsmanship into mathematical perfection. Warner needed to cut a spiral with a constantly changing pitch, tight at one end, loose at the other. The kind of challenge that would make modern CNC programmers reach for calculus and parametric equations. But The Cincinnati Universal Milling Machine in front of him had a mechanical solution that predated differential equations by half a century. The differential indexing attachment looked like a small automotive differential transplanted into a machine tool. 2 inputs, 1 output, feed rotational motion into both sides simultaneously, and the device would add or subtract those rotations, creating compound angles that varied continuously as the cutting progressed. Warner connected the table's lead screw to 1 input, driving it from the normal feed mechanism. The second input he connected to a hand crank. As the table advanced under power, he would slowly turn the crank, adding rotational bias to the workpiece. The differential summed these motions mechanically. No math, just planetary gears orbiting inside a cast iron housing. The result was pure mechanical calculus. The spiral's pitch changed continuously as Warner adjusted the hand crank's speed, creating curves that would challenge analytical description but emerged naturally from the machine's kinematic chain. The workpiece didn't know it was integrating motion over time. It just followed the geometric constraints imposed by meshing gears. In Fitchburg, Massachusetts, Pratt & Whitney's jig borer was pushing positional accuracy to limits that electron microscopes wouldn't exceed for another 50 years. The machine located holes using a microscope mounted to the spindle, positioning the table through precision lead screws threaded to 50 threads per inch and read by vernier scales divided to 10,000ths. But the real precision came from the machine's kinematic design, the way its bearings and ways constrained motion to exactly 2 perpendicular axes. George Norton, the designer, understood that accuracy wasn't about measuring small numbers. It was about building geometric relationships that couldn't physically vary. The jig borer's table rode on hand-scraped boxways. 4 surfaces ground and scraped until they defined perfect perpendicularity through mutual contact. No laser alignment, no computerized measurement. Just Prussian, blue dye revealing high spots that machinists scraped away until the geometry satisfied itself. Warner had seen machinists bore holes on the jig borer that came back from inspection marked 0.003 inches, 30 millionths over nominal, measured on gauge blocks whose accuracy traced to the National Bureau of Standards master blocks in Washington. Precision achieved without electricity, maintained through geometric relationships that would outlast the building that housed them. The machine computed positions through the direct mechanical connection between lead screw rotation and table translation. Turn the handle 0.020 rotations. Move exactly 0.0004 inches. The mathematics lived in the thread geometry, not in any calculation performed by the operator. In the Pratt & Whitney gauge room, master thread gauges hung like sacred texts in a temperature-controlled vault. Each one represented thousands of hours of hand-lapping and measurement, creating physical standards that defined what threads should be before anyone had computed their theoretical profiles. Margaret Fletcher, one of the few female precision inspectors in Hartford's Tool District, selected a master gauge for 1-2-13 UNC threads, 13 threads per inch in the Unified National Course Series. The gauge had been made in 1908, its threads lapped by hand until they mated perfectly with gauge blocks and sine bars that established the theoretical 60-degree flank angle. But here was the profound truth that separated 1915 manufacturing from modern practice. The master gauge wasn't made to match calculated dimensions. The calculations were derived from the gauge. The physical object came first, refined through mechanical processes until machinists agreed it was correct, then measured to establish what the numbers should be. Fletcher inspected a production thread gauge, comparing it to the master using a technique called feeling the bearing. She'd oil both gauges, screw them together, then sense the resistance as she rotated one against the other. Too tight, and the production gauge was oversized. Too loose meant undersize. Perfect mating produced a specific drag that experienced inspectors could feel through their fingertips. Mechanical precision transmitted through human nerve endings. The wage inspectors at Brown & Sharp used optical comparators that projected shadow profiles onto ground glass screens marked with master outlines. But even these devices compared physical objects to physical masters. A gear's profile wasn't right because it matched an equation. It was correct because its shadow aligned with the shadow of a master gear that had been proven in service. This created fascinating philosophical problems that engineers of the era wrestled with. How do you know the master is correct? They verified it against other masters made by different shops using different processes. If three independent masters agreed within measurement uncertainty, they probably represented the theoretical ideal. Warner remembered watching Fred Kingsbury, the legendary gauge maker, create a new thread master using nothing but lapping, compound, and infinite patience. Kingsbury would cut the thread slightly over size, then spend weeks lapping it against a mating gauge while checking pitch with a traveling microscope. The thread emerged from this process not computed, but evolved, refined through comparison and adjustment until it satisfied geometric ideals that calculations could only approximate. No computer could have created these masters because their accuracy exceeded what measurement could verify. They existed in a realm where geometry became more real than mathematics, where physical objects defined truth that equations struggled to describe. The masters taught the machines, and the machines taught the machinists, passing precision down through generations of mechanical contact. The overhead line shaft ran the entire length of the Bullard machine tool factory floor. A spinning steel beam supported every 20 feet by hangers dropping from the ceiling trusses. Leather belts descended from this shaft to individual machines, each one connected through a stepped cone pulley that let operators select from 5 different speeds without stopping the shaft. Samuel Cross, floor supervisor, walked the production line, listening to the rhythm of 30 machines, all drinking power from the same rotating source. A belt slapping meant tension adjustment needed. A squeal indicated misalignment. The symphony of synchronized production played in leather friction and bearing whir. But the line shaft was more than power distribution. It was a mechanical clock that coordinated production timing across the entire factory. When Cross needed to slow production because raw material delivery was delayed, he didn't reprogram individual machines. He adjusted the steam engine's governor, slowing the shaft and every machine connected to it simultaneously. The belt system embodied analog control principles that digital systems would later rediscover. Tight belts transmitted full power. Loosen the belt tensioner and the belt slipped, reducing power transmission while maintaining speed. Machinists used this property as a crude clutch, adjusting belt tension to control cutting forces without changing spindle speed. Cross remembered the factory before the line shaft, when each machine had its own steam engine. The coordination nightmare of maintaining 30 independent power sources, the fuel waste of running engines at light load, the impossibility of synchronizing operations that required precise timing relationships. The line shaft solved these problems through mechanical simplification. One large engine ran efficiently at optimal load, power distributed through rotating shafts reduced to exactly where needed, maintenance concentrated at the central power plant rather than scattered across individual machines, but the system imposed constraints that shaped how machinists thought about production. You couldn't speed up one machine without speeding up everything on that shaft segment. Production scheduling became a geometric puzzle, arranging operations so that machines sharing shaft segments ran at compatible speeds. Some operations required timing synchronization that the line shaft provided naturally. Transfer machines that moved parts from station to station used mechanical indexing driven by the same shaft that powered cutting operations. The part advanced, the tools cut, the part advanced again, all coordinated through gears and cams rotating in fixed relationships to the master shaft. Cross had visited the Ford Highland Park plant, where Henry Ford was perfecting the moving assembly line. Same principle at massive scale, a mechanical pacing system that coordinated hundreds of operations through pure physical connection. No electronic controls, no programmable logic, just rotating shafts, chains, and conveyors moving at speeds dictated by engine governors. The line shaft was the factory's nervous system, carrying both power and information through the same rotating medium. Warner stepped back from the completed rifle barrel, its 29 threads per inch cut with an accuracy that optical inspection confirmed to within 0.005. The Hendy lathe had transformed rotating motion and bronze gears into helical geometry precise enough for military specifications. No computer, no electricity beyond the shop lights. He hung the change gears back on their pegs, each one marked with tooth counts that represented fractional relationships in mechanical form. The gears would outlast him, would outlast the building, would still be cutting threads when people had forgotten why 127 teeth unlocked metric conversions. Margaret Fletcher locked the master gauges back in their vault, temperature logs showing the room held 68 degrees within half a degree. The masters would be there in 50 years, in 100 years, physical standards against which future generations would calibrate their own work. Paper blueprints might yellow and fade, but these hardened steel artifacts would carry precision forward through direct mechanical inheritance. The line shaft overhead spun at 200 RPM, same speed it had turned since installation. The leather belts would wear and be replaced. The bearings would be oiled and adjusted. But the system's fundamental architecture would persist until someone decided to rip it out and install individual electric motors. A change that would come in the 1920s, but would sacrifice the coordination that mechanical connection provided. These machines embodied a different philosophy than what would follow. They weren't programmed to perform tasks. They were structured to make certain tasks inevitable. The geometry lived in the iron, the intelligence in the mechanical relationships, the programming in the ratio of bronze teeth. When Warner's grandson would work in the same Hartford factories 60 years later, he'd operate CNC machines that could cut 29 threads per inch by typing numbers into a controller. Easier, faster, more flexible. But when the electronics failed, the machine would sit silent until replacement parts arrived from overseas. The Hendy lathe would still be there, relegated to a corner, still capable of cutting threads with the same precision it delivered in 1915. No obsolete software, no discontinued control boards. Just geometry enforced by mechanical constraint, waiting for hands skilled enough to use it. Warner cleaned the ways with an oil-soaked cloth, the same ritual machinists had performed since Maudslay first scraped iron to precision. The machine didn't need him to understand it. It just needed him to maintain the geometric relationships that gave it purpose. So if gears, cams, and pure geometry could achieve precision that modern computers still struggle to match, and if these mechanical solutions were immune to software, obsolescence, electronic failure, and proprietary lock-in, why did we abandon them?